Jamie,
Yeah. So
I'm going to talk for 40 minutes,
good.
and I would like to have a signal every 10 minutes.
Okay. Good afternoon. What a great crowd. I'm Farnham Johanyan, Provost here at Carnegie Mellon. On behalf of the CMU community, it is my pleasure to warmly welcome you to Carnegie Mellon's Dickson Prize Award presentation and lecture today. I want to thank all of you for joining us. I first want to acknowledge and thank Professor Emeritus Guy Berry and the Dickson Prize Committee for making such an excellent choice in the selection of this year's honoree, Dr. Judea Pearl. I would also like to thank Randy Bryan, our former Dean of School of Computer Science. Randy is our faculty host for this year's award, and also the faculty colleague who nominated Professor Pearl. Let me first say a few words about the Dickson Prize. The Dickson Prize lecture is one of Carnegie Mellon's most important scientific events of the year. One that not only honors leaders in science for their accomplishments, but also marks important trends and new directions of scientific thought. The Dickson Prize in Science at CMU, and there's also a Dickson Prize in Medicine at the University of Pittsburgh, were established by Dr. Joseph Dickson, who was a prominent Pittsburgh surgeon, and his wife, Agnes Fisher Dickson. With this prize, Dr. and Mrs. Dickson hope to bring as much prestige and honor as possible to the two universities and to Pittsburgh. Carnegie Mellon has been awarding the Dickson Prize to leading scientists since 1970. And year after year, we've been able to bring some of the world's most prominent and thought leaders to our Pittsburgh campus. This procession of renowned scholars over the last 45 years has allowed us to chronicle and pay witness to incredible advances in natural sciences, engineering, computer sciences, and mathematics. The Dickson Prize recipients the Dickson Prize recipient we're honoring today, Dr. Judea Pearl, exemplifies this tradition brilliantly. For more than 50 years, Dr. Pearl has been at the forefront of advancements in computer science and machine learning, the areas of very significant research activities at CMU. Over the course of his brilliant career, Dr. Pearl has made extraordinary contributions to computer science and artificial intelligence. Like many previous Dickson Prize winners, his scientific research has had implications and applications for a wide range of disciplines and applications. In fact, his influence extends far beyond artificial intelligence and even beyond computer science to human reasoning and philosophy of science. Dr. Pearl is best known for championing the probabilistic approach to AI and his pioneering work in Bayesian networks, a mathematical formalism for defining complex probability models. He has been credited with helping to create a mathematical framework for causal inference, which has revolutionized, and I quote, the understanding of causality in diverse fields, including psychology, medicine, econometrics, and social sciences. For those of you in the room who are not familiar with the work and are not computer scientists, let me just explain this in sort of a more straightforward term. The introduction of Bayesian networks is one of the most important developments in our field. Before Dr. Pearl's work, most artificial intelligence systems reasoned with Boolean logic. That is, they understand true or false. But the major difficulty that we address is that you have to be able to reason not just true and false, but also maybe. Yet modern AI systems such as speech recognition, image analysis, natural language understanding, and automated translation, in fact, most interactions that we have with the physical world routinely encounter uncertainty. Dr. Pearl's development of Bayesian networks therefore created a theoretical foundation for reasoning under uncertainty and marked a critical step in achieving AI that can interact with the physical world. He essentially helped us to give machines the ability to reason in shades of gray, not just black and white. This, of course, revolutionized the field of artificial intelligence, but also became an important tool for many other branches of engineering, natural science, health sciences, social science, business, economics, and so on, with broad range of applications in medical diagnosis, genetic counseling, mapping gene expressions to natural language understanding, autonomous vehicle, and the list goes on and on. For these many accomplishments, Dr. Pearl has received an impressive list of accolades and awards, too many to enumerate. In 2004, he received the Alan Newell Award for seminal contributions to the field of artificial intelligence that extend to philosophy, psychology, medicine, statistics, and social sciences. In 2008, the Franklin Institute awarded him its Benjamin Frank Medal for the creation of algorithms to help compute and reason under uncertainty. For my fellow computer scientists, you know that in 2011, Dr. Pearl was awarded the Association for Computing Machinery's A.M. Turing Award, also known as the Nobel Prize in Computer Science, and I quote, for fundamental contributions to artificial intelligence through the development of a calculus for probabilistic and causal reasoning. I want to digress for a second and tell you how I met Dr. Pearl. Of course, I knew of his work for many, many years. I had arrived to the National Science Foundation. It was like a week into my arrival. And Howard Rockler, who's here, Howard, where are you? Who's here? And he was serving as the division director for IIS, comes to me and says, Farnham, Judea Pearl was just won the Turing Award, except we just declined his proposal. Well, first of all, for those young scientists here, if your research is declined by National Science Foundation or NIH, you're in good company. First, start with that. But the last thing you want to hear as the brand new director for SCIES is that National Science Foundation turned down the research of a prominent scholar and our Turing Award winner. But the news got a little bit worse. And the story was that, in fact, we had been funding Dr. Pearl's research since the late 70s, I think. Every 3 years, a proposal and topics related to his area of research got funded. From the late 70s until 2011, the year he received the Turing Award. There's a moral to this. By the way, we fixed it right away. And Judea can tell you all about that. But there's a moral to this story, actually. The fact that this is what science is about. You spent decades working on problems that, in fact, the practical applications of it may not be known. And you do sustained work in areas of exploration. And eventually, they come to fruition. So that's the story about the Turing Award winner. And I've been a huge fan of course, Dr. Pearl for many years. Just a couple of more notes, and I'm going to invite Dr. Pearl to join me on the stage with Randy. I should also add that he's a member of National Academy of Sciences and National Academy of Engineering and many, many other fellowships that he has received. It is my great honor to have Dr. Judea Pearl here with us this afternoon to accept the 2015 Dickson Prize in Science. He has traveled all the way from California, where he serves as the Chancellor's Professor of Computer Science and Statistics at UCLA, and also directs the university's Cognitive Systems Laboratory. At Dr. Pearl's request, the part of Dickson Prize, cash prize, I should say, part of it will be donated to his alma mater, Technion, the Israel Institute of Technology, and part of the funds goes to Daniel Pearl Foundation, which was created in the memory of his late son, Daniel. Before we're treated to his lecture, I want to invite Dr. Pearl and also Dr. Bryan to join me on the stage for conferring of the Dickson Prize medallion and award check. Please join me.
Congratulations.
On behalf of Carnegie Mellon University, it's my honor to present you with the Dickson Prize for many contributions that you have made to the field of artificial intelligence for the past several decades. It's a pleasure to have you here with us.
Thank you very much. I guess I have
You don't have to wear it today. No, you don't have to wear it today.
It's quite heavy.
It's a nice big one, yeah.
Thank you.
Congratulations.
Judea, we look forward to your presentation.
Thank you. It's a really honor for me to be here again. You know, Carnegie Mellon has has a soft spot in my heart because it is here that I left the green pastures of reasoning with uncertainty and went to fight the uphill battle of causal reasoning under the influence of your philosophy department, people like Clark Gilmore and Peter and Richard Shine. So it is a great honor for me to be honored by people who can read your papers. This is a unique occasion in our world. What I would like to do is to give you I have 40 minutes, so I decided to divide it into 4 parts as articulated in my outcome, and there should be a, yeah, here it is. I hope I'm pressing on the right button. It should be advanced here. Here it is advanced. Yeah. Yeah, the title was chosen to be both provocative and to interest a broad audience, because I know that you have here great people working on computer science and philosophy and statistics. And actually, it's unique to Carnegie Mellon that I found here harmony among the 3 departments that I just mentioned here. Normally, they fight with each other, and for good reason. But here I find harmony, so it's great. So my outline is going to be first the causal revolution. There has been a revolution in the causal reasoning business, and you can tell it by various indicators. For instance, people know nothing about causal inference, put on the resume causal inference. And this is a sign that it is a merging field. And then I'm going to talk about 2 fundamental laws of causal inference. I chose them to be fundamental. Other people may find other derivatives to be fundamental. But the point is that if you master these 2, if you remember them, you can derive everything that I've done, and I think everything that I will ever do. I'm quite old. So then I'm going to go to application area and give you a rundown of the many problem-solving derivatives of this theory. And here I'm going to divide it into the old, namely those that you can find in the literature, and those that are just, and the new, which just came out, I mean by 2 or 3 years ago. And I will end with a couple of thoughts about the free will illusion. So we have a timekeeper here. Please give me a signal. 10 minutes. I'm going to talk for 40 minutes, 10 minutes each. So give me a signal at the end of 10 minutes. Who am I going to watch? Andy? Okay, thank you for volunteering. Yeah, so what's the causal revolution? It's essentially the scientific revolution. And something happened about 10,000 years ago. in his book, Daniel Dennett makes an observation that 10,000 years ago, human beings accounted for less than 1% of all vertebrate life on planet Earth. And today, the percentage has gone up to 98. Okay. In the evolutionary scale, it's a blip. 10,000 years is nothing. So there must have been some quantum change in the cognitive structure of humanity. What happened? One hypothesis is, and I buy that, for computer science, this is a question. There was some computational facility that humans possessed, either a result of some cosmic radiation or natural mutation, but something happened there that did not happen for millions and millions of years ago. And it happened to us and not to any other organism. Strange. And one hypothesis is that about 70 years, that you can tell it by looking at the advantages that the sapiens had over the Neanderthal people. About 70,000 years ago, the Homo sapiens migrated from Africa to Europe and Asia, and they wiped out the Neanderthal inhabitants. And the question is, what is the secret of their success? So one theory here that I found is in this picture. They were able to imagine the impossible. Here you find an ivory figurine which shows a lion head hooked onto a human body. Such creatures do not exist. But the sapiens, that was found, by the way, in a cave in Germany 32,000 years ago. And it was found recently. It is dated 32,000 years. Okay? And here it is magnified. You can see a lion head and a human body. Creatures like that do not exist. And the theory is that it is the first indisputable example of the ability of human mind to imagine things that do not really exist. So how is it connected with the computational advantage over those who didn't have this facility? One theory says that it enables you to make promises and to trade with promises, which means you can tell people, if you pay taxes, I'm going to protect you. Okay? And the promises, people trust that promise. A ruler can come up and say, give me your sons for my army, give me your daughters for slaves, and I'm going to protect you. And you believe that rumor. More than that, somebody can tell you, I'm going to promise you afterlife. And you believe that person. What is it called? It's called that trade in promises. It's a cohesive cement that creates large community. You can hunt better, more effectively, greater mammoth. Okay? You can form villages. You can form empires. Okay? Harari makes this point. And he says, you can teach a monkey many things. You can teach him to jump from tree to tree, to cut a branch in one tree and get banana on another tree, right? All this you can do, but one thing you cannot do. And this is to give him a promise about afterlife. And people do. And you know what happened with religion, okay? That empires, it happens because of this ability to trade with promises. By the way, it happens in the idea of economics. We trust the Wall Street for what it is. Right? It's the idea of capitalism, and it works. So there's another thing that happened there, and it happened together. It was about 7,000 years ago in Greece. And this was a development of mathematics to assist with the representation of the world that we have. Because ability to think about the impossible requires that you have a model of your world. You have a model of the world and which you can modify without actually modifying it in the physical world. And the Greek invention of the axiomatic system for geometry was another layer on the ability to represent the world. And it gave Greek the idea that you can obtain knowledge by the act of intellect. It happened together with a Greek style of metaphorical reasoning. It didn't happen by itself. And the philosopher Tolmin makes a nice observation. He says that the Babylonian superseded the Greek scientists in terms of accuracy and reliability. They could predict the eclipse of the moon much more accurate than the Greek. But the Greek philosophers had something that the Babylonians did not have. And this is metaphorical, imaginative, creative, speculative reasoning. They believe that the sky is made of opaque shell in which the stars are holes poked in that so we can see the eternal light, and we walk on a turtle shell which is half spherical. These are speculative. Actually, we know that are wrong, but they were familiar. You are familiar with holes poked. You're familiar with turtle shells. And that's what gave Eratosthenes the imaginative push to say, if I'm walking on a turtle shell, then it has a radius. And if it has a radius, I can measure it. And I'm going to go down to the Aswan Dam there and find a well, which is a different angle than the well in Alexandria. I'm going to measure the difference between the two angles, and I know the distance. I'm going to measure the radius of the globe, of the Earth, namely the turtle shell. That kind of speculative reasoning would not occur to Babylonians who predicted the eclipse of the moon by curve fitting. Okay? Black box, very accurate curve fitting. That's what the Greek had together with the axiomatic system. How did they value the axiomatic? I had one theory that it came from democracy. They argued and argued in the Acropolis, and they were tired of arguing, and they were seeking some sort of a coherent framework in which the truth can come out. So from over-arguing, they invented the axiomatic system for geometry, okay? But that's a theory, okay? The basic element here is that you have to have a blueprint of reality which enables you then to manipulate it without actually doing so. So you can figure out the volume of the pyramid without actually measuring it, and you can modify the design of your boat without actually loading it and see at what point it fails. And so I'm going to talk about this control over the environment, which eventually leads to a control over oneself. Because if you have a model of the environment and you have a model of yourself, just a sketchy blueprint, not a model, right? Then you can answer counterfactual question and come out with an interpretation of this sentence, I should have done better. So this is a scheme of my talk. Alan Turing was the first, I think, that made the connection between evolution and machine learning. And in his paper of 1950, he said, survival of the fittest is a slow method of measuring advantage. The experimenter, in his case, it was a programmer, okay, by exercise of intelligence, should be able to speed it up. How? if he can trace a cause of some weakness, he can probably think of a kind of mutation which will improve it. And that is, I believe, the role of counterfactual in the context of machine learning. So I'm going to focus now on causal reasoning, because I think this is a very fancy modality that I thought contains the secret to machine learning problem. And it is a very diverse kind of modality. It is the basis of human cognition and ethics, scientific thinking, robotics, and many, many data-intensive scientific applications that in which we can find thousands of potential beneficiaries that were unfortunately educated on traditional textbooks and therefore cannot solve the basic problems that have a causal element in them. Human cognition and ethics, all I need to show you is Adam and Eve. And you know the story that God asked Adam, hey, did you eat from the tree I told you not to eat from? And Adam, look what she said. She handed me the fruit and I ate. Okay? God asked for the facts and you come up with explanation. Okay? And Eve, likewise, the serpent deceived me and I ate. So according to the Bible, at least, it's a very deeply entrenched tendency to provide explanation, even down there in the Garden of Eden. And counterfactual. The first counterfactual I found in the Bible was connected with Abraham. You know the story when God told Abraham what he's about to do to the wicked city of Sodom and Gomorrah. Abraham said, you can't do that. השופט כל הארץ לא יעשה משפט. That's how it went in Hebrew, which means really, I'm going to smite the wicked and the righteous. And the question he was asking, what if there were 50 righteous men in the city? Okay. And God said, no, I'm going to spare the city if I find 50. Now you see, they're talking about the impossible. God knows how to count, right? And God knows how to distinguish the wicked from the righteous. So what is if I found? And the story goes even further, that Abraham asked him, 50, what about 45? I'm not kidding. And God says, I'm going to spare, are you going to make a big fuss of 5 people? And it goes down to 40, and then 30, and 20, and 10, and we know what happened. And the question is, what is Abraham haggling for? He trusts God, right? I think that the interpretation is that Abraham was the first scientist. He was looking for the general rule. The general rule, not only this to city, the general of collective punishment. Under what threshold makes a city responsible for its extremes elements? In that respect, he was the first scientist, because science is all made of counterfactuals. And let me convince you that a simple rule like Hooke's law, that Manuela asked me to talk about it, that all physics rules and the way we teach physics in high school is all about counterfactual and not about algebraic equation. Here is an example of a simple rule. If you hang a weight of 1 kilogram, the spring is going to be 2 times x 2. Right? And according to algebra books, 2 systems of equations are algebraically equivalent if they preserve solution. So this system of algebraic equation is identical, equivalent to that one. The question that I ask you is, are they really identical? Do they convey the same information? The same thing here. And the answer is no, because from the one on the left, I can answer counterfactual questions that I cannot answer from the ones on the right. For instance, what if the weight was 3? Every high school kid can solve it. Okay? You wipe out the x equal to 1, you replace it by x equal to 3, You substitute in the top equations, and up you go. Okay? X is equal to 1 and y is equal to 2. You cannot do it here. You cannot do it here. Why? Because here, what the high school student is doing in his head is he knows which equation to wipe out and which equation to treat as a general rule. Okay? If you give it to a robot will say, wait a moment, contradiction. Just told me x is equal to 1. Now you're going to tell me x is equal to 3. And there's something where I can do here and I cannot do here. This is the wiping out. If I wipe up here, x equal to 1, and replace x equal to 3, I get the correct answer. If I do it here, and I wipe here x equal to half y, and replace it by x equal to 1, I will not get the right, I will not get the right answer. So there is something about the wiping of equation, the recognition that one equation stands for general rule, the other one for boundary condition, that allows the students to solve physics problems in high school. And that's all we do it in the speed of light. And the question is, if wiping is the process, then we have to build an algebra for wiping. If you give it to a robot has to know exactly what to do at any point. You cannot tell him, I can't lead him. Okay. So the correct interpretation of physical equalities is really an assignment. The length variable is listening to the weight variable and assign a value to it according to what it sees in the other variables. So that is a language of science, not the language of algebra. And then when it comes to robotics, after I convince you that science is all counterfactuals. Here's the robot that I like to present, which is faces problem of handling messy laboratory or messy kitchen, and it ought to have a causal understanding of what's going wrong in order to repair things. And it's not an easy thing to even teach the robot what needs to be repaired or what the causal relationships are in the kitchen, because because it is not a simple rule-based system. Causal reasoning cannot be based on the rule and on chaining rules. I have my favorite example. If the grass is wet, then it rained. If I spill this bottle, the grass is going to get wet. And it's not true that if you spill the bottle, then it rains. Okay? So rule chaining is not the right way. You need to do it correctly. Suppose we do teach a robot cause-effect relationship in the world. What kind of questions we want him or her to answer? First, observational questions. What if I see A? It's called evidential reasoning. If I see something, I want to infer something. If I see symptoms, I want to infer a disease. Okay? And then you want also the robot to answer action questions. What if I do A? And the third one is counterfactual. What if I did things differently? So I did something, you saw the results, and what if I see things differently? Okay? These are the three layers of the hierarchy which I'm going to talk to today. They are distinct layers in the sense that syntactically or logically, you cannot infer any conclusion in layer I unless you have assumptions in level I or lower, in this case. So you cannot answer any questions about intervention if you have just statistical information. You have to have some causal information in the system. And if you want to be really fancy, you can decorate it on this probability, but that's not the point. The point is that you have a causal hierarchy that is logically distinct. So I'm going to run now a Turing test on the causal modality. We have to demonstrate the three layers. The Turing test is going to be the computer behind the screen here. Here is the interrogator, Mr. Interrogator. you are here asking question, and the task is for the machine to answer simple toy-like questions about a toy-like story, but dressed in causal vocabulary. And first question, here's the story. The game is you tell a story to the machine, and you want to get a reasonable, plausible answer. Here's the story. I use this many times in my book and other things. You get up at your house, and the pavement is slippery or wet, and you know that it can be wet either because the sprinkler is on or the rain is on. Very simple story. First question I want to ask is, if the season is dry, and the pavement is slippery, did it rain? This is an evidential reasoning type. Okay? You saw something, you want to infer the degree of belief in something else. And you expect an answer like that. Unlikely, it's more likely to be the sprinkler was on, with a very slight possibility that it is not even wet. If you have the probabilistic model, and many of you understand that I'm heading there, right, then you can dress it up with a vocabulary like that. But first you have to have the essence encoded in. Then you go, but what if I see that the sprinkler is off? So here you have a change of evidence, and you expect that it's more likely that it rained. Beautiful. Now we go to action. Do you mean that if we actually turn the sprinkler on, the rain will be less likely? And you want the machine to say, hey, we're talking about action here. Action is different than seeing, okay? If you actually turn the sprinkler on, then it's, the likelihood of rain would remain the same. The rain doesn't listen to your sprinkler. Okay? And then you come to counterfactual. Suppose we see that the sprinkler is on and the pavement is wet. What if the sprinkler were off? Here you are using what you see in order to make inference about the past, about the rain. And the answer is the pavement would be dry because the season is likely dry. How do you know the season is dry? Because you see the sprinkler is on. Okay? And now you change it. Now this is all plausible, right? This is kind of behavior you want. Do you think it is easier to program? In order to program that, you have to understand what it means to, for the rain to be a result of the season, for the wetness. What cause-effect relationship mean? And in the time of a few years after Turing, the philosopher Chancellor said, passing the Turing test doesn't mean that you understand. Because I could have a Chinese book, and I can just read from the rule. Here's my Chinese book. It tells me for every question, I can look up the book and look at the answer. Okay? So Several believe that his Chinese book refutes the idea that passing the Turing test is a sign of understanding. But what Several forgot is that there aren't enough molecules in the universe to make up this Chinese book. Okay? So you can say, is it the case just the fact that you beat the combinatorial expression a proof of understanding? And the answer is yes. Because what is understanding? It's the ability to take advantage of the constraints of a domain, both syntactic and semantic. You cannot do it if you don't have the semantic and the syntactic constraint. So therefore, it is a necessary component. And even for the sprinkler example, if you think about how many lines of code you need to use to satisfy the Searle Chinese book case, in order to answer the question about the toy-like sprinkler and the season, you find out you get into trillions right away, because every subset of variable could be an action. Every subset could be an antecedent of a counterfactual. So right away, you count the number, you multiply the number of subsets, each one is exponential. If you don't have a semantic, you cannot answer even the sprinkler problem. So the name of the game is to run a causal conversation, we need to have a parsimonious description of a domain. And now I come to the reasons why I spent the last 10 or 5 years of my life away from robotics, away from scientific thinking, into the data-driven applications, because there are so many people who could take advantage of every insight that we get from the causal understanding science. And most of the people who are working today in the data-driven sciences were educated on the basis of traditional statistical paradigms. And I know there are many statisticians here, so I wouldn't be insulting, revealing to them what they know. That this paradigm has ruled data-driven sciences. You know? From 1834, when the Royal Statistical Society came out with a manifesto of its mission. And the mission was, we will not publish any paper here which is based on your opinion. Data, data, and data. This is all we are going to focus on. And that has been taken up by Fisher, who defines statistics as a method of reducing data. And it's been going on for up to our days. I can prove it if it got up to date by just asking you how many statistics textbooks you have which deviate from that paradigm. Very few. So the basic paradigm of statistics is that statistical concepts are those that are expressible in terms of joint distribution of observed variables. All others are marginalized, you know, from statistics proper. They have names, substantive matter, domain dependent, metaphysical, ad hoc, and so on, but away, don't bother me. It's essentially ruling out all of science except for the first layer, which is evidential reasoning. And surprisingly, even my machine learning up to date, still working on the first top layer, which is evidential reasoning. Give me evidence, I'll modify something, I'll get a bit of it. Bit of it, bit of it, bit of it. There have been some awakening with the Neyman invention of the notation of counterfactual and Rubin popularizing it and attaching to that variables and the idea of ignorability and some inference machinery. But essentially, statistical education at large is infected with causalophobia. And I understand why. How can you ask a statistics instructor to teach causal inference if the statistics instructor remember his or her professor blushing when the time came to talk about causality? That's why it takes science, generations. If you remember your professor embarrassed in a certain topic, you don't teach that topic. And that's how it goes, generation after generation. Okay, we are inflicted with that tradition, with that inertia, but we are making progress. I bring it here at this point because Plato cave reminds me of statistics. Statistics is the study, is the logic of the shadows on the cave wall. Where in reality, you have the three-dimensional objects which are reflected on the cave wall. And this is a causal understanding of the world. I think I did, yeah. So, passing the Turing test for causality. What do I propose? I'm 20 minutes after? Okay, I'll go quickly on that part because I have to get to the two basic laws of causal reasoning. Okay. I'm replacing now the oracle that used to be joint probability distribution with another oracle, and this is a structural causal model. All it is a collection of functions, the physical way of perceiving, the physics way of perceiving the physical world. That each variable, think about these variables. Okay, the sprinkler listens to the climate, the rain listens to the climate, the wetness of the pavement listens to them. It's a collection of functions, and that will choose a value for your variable, okay, depending on the value that you see in other variables. There's nothing there but a society of listening and responding agents. Once you have it, this is the oracle of everything we need. Of course, in reality, we will not have the function, we'll have things missing. Okay? But once we have that, then we have a parsimonious encoding of counterfactual knowledge, and I'll show you how you can derive counterfactual from that. And it's a new oracle. It's replacing the traditional joint probabilities of observed variables. It turns out that if you have that you can generate all the counterfactual that you want. Simply, you interpret, here it is, 3 equations. If you're asking me for the value of y, that y would have, had x been small x, all I have to do is to cut off the arrow going from u to x, all the parents of x, and just assign to y whatever value, whatever solution for y is when you keep x constant. Okay? So you replace the equation for x with a constant. That's all there is for computing counterfactual. Every high school kid can do that because every high school can solve equations. So if you have the model of the world, total model, with all the functions they're specified, to find the counterfactual, you just compute the counterfactual after you mutilate the model and you replace the equation for x with the antecedent, small x. That's all there is. So this is the fundamental equation of counterfactual. And I want to emphasize here that there is a puzzle about counterfactuals. We communicate with counterfactuals. We understand it actually with counterfactuals. And here is a classical example by Adams from Berkeley about how people communicate and how people form a consensus. If I tell you that if Oswald did not kill Kennedy, then someone else did, you say, yes, you're right, I agree. If I tell you that if Oswald hadn't killed Kennedy, someone else would have said, no, that's not so good. And people agree uniformly, no matter where they reside, no matter how small knowledge they have about the politics and situation in Texas in 1963, they would agree to that. How come they agree to that? What do they have in common that we all feel yes on the first and no on the second? And that is, it's really should be obvious that the answer is that we have a mechanism, that we share a mechanism for reliably computing counterfactual. Otherwise, we wouldn't agree. And it's amazing that even Hume and a great philosopher like David Lewis did not come up with this puzzle, did not respond to that puzzle. Hume defined here causation in terms of counterfactual, which is fine. Okay? Here's a definition of a cause. David Lewis, too, he defined A causes B in terms of were not for A, okay, counterfactual. And the question is, why are they defining cause in terms of counterfactual and not the other way around? It must be that the counterfactuals are easier to compute, more reliably, more uniformly. Right? That is my question. And I think the proposals by David Lewis doesn't answer this question because his definition of counterfactual has to do with the perception of degree of proximity between worlds. You know how many worlds there are in the world? And you know how many pairs of worlds for which you have to assign degree of closeness? It's unbelievable. Okay, it's not unbelievable. It's nice theory, it's nice logic, but it doesn't give you an answer to how come we communicate with counterfactual. So I think my proposal answers that, and this is the first fundamental. Here it is. Now the second one, which is the law of conditional independence. It so happens that no matter what the functions are, nature, nature leaves a signature in what you see. And I'll demonstrate it here. Here's our picture of nature. Every variable has a function that determines its value, but you don't see those functions. All you see is samples taken from a distribution. So you have a distribution on S, C, R, and W. There is a signature of the structure of the model in your data. And the signature is that whenever you have a missing arrow in the structure of nature, you have a conditional independence in the data. Here there is a missing arrow there. Here there is a missing arrow here. Each one advertises a missing, here you have a missing arrow, and they dictate that you have a conditional independence, which is marked this way. And what does it give you? Oh, it gives you many things. Application of that is the following. First, you can test your model. If you don't see conditional independence, where your model says you ought to see, then the model is rejected. And you know how to repair it. And you can do structural learning. I see Clark here. So you can, if you know how to rule one model, then if you have many conditional independencies, you can talk about a set of models which remain after you rule out all the bad ones. And the set may be small, workable, and they might all agree on a causal question. So that leads to the possibility of structural learning, and more. You can reduce the question. What if I do? To question about symbolic calculus. You can derive it by symbolic calculus, and you can do a lot of scientific questions reduced to symbolic calculus. I come now to the area where I give you a sweep of these applications and to try to convince you that they are not as hypothetical as my counterfactuals. They are real-life applications. The first of them is, here they are listed again, and I need to find it, yeah. Okay. I'm just going to go over these 6 very quickly. Gives me a minute and a half for each. Okay. First is policy evaluation. Who doesn't want to do policy evaluation? You have books written on it. Evidence-based policy evaluation, all kinds of things like that. But this is basically, the idea is to reduce policy evaluation question to symbolic calculus. So you can derive it like we do in calculus. Yeah? And here's an example. What if we bar cigarette? What is the probability of cancer given that we do smoking or we do not smoking? Action. The logic goes through a set of rules and reduces the query, this is what we want to find out, probability of cancer given that we do smoking, into something that we can measure. And the thing is we can measure are things without a do. Because if you have data without intervention, if you don't want to force people to smoke or not smoke, right, then you have to rely on your observed data. What is the observed data? Probability expression, you see, with the Bayesian conditioning bar advertising itself. Condition on X. This is done by regression. This is done by statistics. So the task is to take your question, which is sophisticated, about hypothetical intervention, okay, and to reduce it to something that is supported by the data that you have. You go through the rule, and if you succeed in removing all the pink stuff, then you succeed in answering the query. What will happen? What's the rate of cancer if we ban cigarettes? Okay. And here, I don't go to the rule, but believe me, there is a machinery, a free rule, that you apply them sequentially, and if you get the right results, or if you succeed in removing, in bringing it into a format that comply with what the data can give you, then you're done. Then you know how to estimate it. You give it to the next department, which is the Department of Statistics, and you ask your colleagues, can you estimate that? Estimate. Then we harness of the 150 years of statistical estimation, and we're in business. Moreover, you can imagine that you have more sophisticated questions. Suppose I can intervene on, not on smoking, I can intervene on, let's say, advertising cigarettes. So you have another intervention someplace. You have also, in addition to observational data, you also have experimental data. Same idea. Take your logical machinery, apply it, and ask it, dear robot, can you reduce my query to a format in which I can see in my data? In this case, if I have interventional, I'll have a do Z, the Z is advertisement, or do a Q, okay, advertisement. Can I support my query on the basis of what the data format that I have available to me? And this reduction will give you the answer yes or no. It so happens that my students were able to prove completeness for this calculus and were able to reduce it to algorithm. So you don't rely on a set of rules, but you can look at the graph and say, yes, it's doable. Then here is the algorithm. Next, attribution problem. The court and the lawyer for the client claims that his client, Mr. A, died because he used this drug. Okay. Now, this is done every day in tort cases in court, and the definition of liability is right here. Court must decide if it is more probable than not that Mr. A would have been alive but for the drug. But for is a legal name for this liability charge. The legal name for the thinking that the jury or the judge must go through to decide if there is a case for the complaint, for the plaintiff. Can we reduce it to any language for which we have calculus? Yes. Bing. We call it probability of necessity. It's a probability that the counterfactual variable alive, given not drug, will be greater than 50%, given what? Given the contradiction that the guy is dead and he took the drug. Once you reduce it to a formula for which we have a calculus, we are done. What else is missing? Do we have the right data? It all can be taken care of. I mean, once I have a formula and I have a semantics for it, and I can calculate it if I had a complete model, I can ask the question, so I don't have a complete model. I have only data taken from certain cases. Sometimes I have experimental data. Sometimes I have a combination of experimental and observational. I can find out if I have enough information to answer this question, and if not, I can put bound on it. Here's an example. I have example in my book in which the lower bound coincides with the upper bound, and I have here a guilty with probability 1. Mediation. Can data prove an employer guilty of hiring discrimination? This is a matter of computing the direct effect of gender on hiring, mediated by qualification. But we don't want to count the part of the effect which is transmitted through Z. We want only the direct. This is interpretation. As a matter of fact, I'm not the one who interprets it. It's the court that interprets it. And this is what the court says in the case of discrimination. You have to find the probability that the employer would have acted differently had the employee been of different sex or race or so on, and qualification had been the same. Look at it. Would, had been. 3 nested counterfactual. Written by a court. It was a court case by Bethlehem against someone complaining. Bethlehem Steel, okay? And this is how the court communicates. Are we scared because they have 3 counterfactuals? No, because we have semantics for counterfactuals. We put it in a formula, and we are done. Once you put in a formula, the question is whether you have the right information to process it. So here is this definition. The convoluted sentence you find in the court proceedings reduced to a single formula, which is just equal to the natural direct effect. I wouldn't go through it. It has, you see, nested subscript, because you have a nested counterfactual. But it's doable, and indeed it reduces to a nice mediation formula, and it's being used now by hundreds of papers on mediation, if you happen to look at the literature. And this is now the standard definition of direct effect. And the same thing goes for indirect effect. I think I pressed on something wrong. Is it possible? Because it disappeared here. Oh, here it is back. Good. Now I'm going to a different application, which has to do with generalizability. Some people call it external validity. Fancy name there. It was a problem that haunts every data scientist. You make experiments here. Under what condition can you say that it applies to a different environment, to a different population, from mice to men, and sick people to healthy people, monkey, and so on. But the problem is to combine how to combine results of several experimental and observational studies, each conducted on a different population and under different conditions, so that as to construct a valid estimate of effect size in a new population unmatched by any of those studies. Here is how it goes in real life. I want to find out the effect of treatment on outcome in Arkansas. I've never been to Arkansas, but I have some model of the Arkansas population. And I have data from New York and from Los Angeles. Some of them are randomized, some of them are not. Some of them have to do with Spanish-speaking people. And some are done with the college students. How do we combine them to get the results? In this form, it's undoable. But when you reduce it to mathematics, it looks like that. Every population has a model, a graph. The differences between the population can be modeled by this S factor, you see. This, something, I pressed on the wrong one. Here it is. This S tells you that the variable W is affected by X in different way than in Arkansas. So there is another factor here. So you model the differences and commonalities among the population, and then you reduce it to algebra. Same algebra I showed before. And you ask the question, can we do it? It grinds through and gives you the answer in algorithmic form, which I didn't put here, in algorithmic form. Yes or no, and if yes, this is how you tease data from each one of the experiments, Combine them, and this is how you combine them, and that is what the estimate is for that. That's called generalizability. I go to the next one here, missing data problem. It used to be thought of as a statistical problem, right, from the 1970s. Okay? But it turns out, here's the problem. Is there a consistent estimate for the joint distribution of this XYZ variable where some of the data is missing? The M stands for I don't have any data. The patient doesn't recall the location of the accident, and so on. High-income people don't like to divulge their salary. So you have missing data. And the question is, can you still find a consistent estimate of the joint distribution of this? And the answer is, wait a second. There's no universal estimator. Second answer is, given a missingness model, we can tell you yes or no, if there is an estimator, and also tell you how. And giving the missingness model, we can also tell you whether or not it has a testable implication. Because testable implication under missing data is not as simple as testable implication under full data. So that enriches the study of missing data with what? By virtue of the fact that we have the facility to model the missingness mechanism. Here's an example of a graph. It tells you the relationship between the X, Y, Z, plus it tells you what causes Z to be missing. Here I have RZ, missing that on Z. It tells you that variable X and Y participate in the missingness of Z, and so on. If you give me that, then I can find a smart estimator for X, Y, Z, which I couldn't before. And here's an example where I cannot do it, because I have a connection here between Y and RY, and I can tell you yes on these and no on these, and now we are building up a whole map. Give me any graph. I can map it, and I can tell you yes or no and how. So this is what you have in the missing data, all due to the ability to model processes and to manipulate them. Okay. I'm coming now to a blue sky topic, free will, which is, according to John Searle, it is an embarrassing scandal. Why is it embarrassing scandal? Because we haven't done any progress in that problem, he said, for the past centuries. Indeed, you know that the first problem was posed by the Bible, and for instance, I remember Maimonides, he wrote volumes on this issue. And the answer was, yes, God can predict everything and still give you the freedom to do the right things. And this is a contradiction. If God can predict everything, how can you tell me that I still have the freedom? And most theologians just got stuck there. All they did is repeated themselves. Yes, God has this, he has this ambivalence. I agree that there is a contradiction here, but either they limit the predictive power of God, he still gives you the option to decide, or they limit our, or they give us extra freedom, that we have extra power. But when you can speculate on God for many generations, but you cannot speculate about a robot. Today we have machinery, so the question boils down to simple things about a robot. No one would deny that a robot is a deterministic machine. You can speculate of whether God is a deterministic machine. But about a robot, there's no dispute, right? So the question is a robot has a free will? And the question is, I think it's just an engineering problem. What kind of software processes would ordain an action as willed? And where is this label stored? Because the question now boils down to whether a robot would act as if he or she has free will. And how do we find out? Whether there is a Turing test for free willness. And I think it is just engineering problem. If we want to have this illusion of free will, because we're talking about a deterministic machine, right, comes to be attributed to a robot, then we have to understand how this illusion is being created on a software level. There is a clash here, of course, between our belief in determinism of the robot and our very clear sensation that I have an option. We all have this sensation. I have an option of either to touch my nose or not. And I have a very distinct and clear sensation that I have this option. And so it's undeniable. It is a logical clash. And the question, where is it? I think the answer is only a software question. How is this illusion created? And why is it useful? So let me go into some... Many philosophers looked at that and say it's a different kind of illusion. Of course, we have many illusions in the world. Like for example, we see sunset, and we know it's not really sunset, it's the earth turning around the sun. And we live with that and satisfied. We see colors of the rainbow. But the philosopher says, no, this clash is of special character because you cannot get rid of it. You cannot say that this is like a sunset and live with the illusion that you don't have free will. And you tell the waiter, sorry, you asked me for steak or omelet. Whatever you do, I decided. Or whatever happens, happens. The waiter will look at you as a strange individual. You cannot get rid of that. And I think it has to do with the following. My answer is like that. We have in our mind a piece of software which is called agency. It's built on top of the neural architecture. It lives on top of the neural flow of signals, not separate from it, on top of it. And it contains three elements. And by the sequence that they are activated, we get this illusion that we made a decision. Okay? So, and these are very essential components. One component is a model of the environment, which brings with it the ability to do counterfactuals and to feel options and to reason with consequences. Then we have a blueprint of our own software. Of course, we cannot have a complete description of our own software because then you get into infinite regression, right? But you have a sketchy blueprint of your software. Right? And in there you have the elements we normally associate with agency, belief, intent, and desires. And the two of them must live together. And another point is that gives you the idea that you did it. It's not done by the neural signals that lie beneath you. You did it because it sits in the same box, and you consulted the model of the environment while you consulted the agents. And how do you remember? You only can remember it if the memory is part of that. You leave trace in this box, and you say, yes, I consulted the model of the environment. Yes, I consulted the blueprint of your own consciousness. And by virtue of leaving this memory trace, you label an action, it was willed. And now comes the question of what computational advantage we get from communicating in this crazy language. Language of credit and blame, guilt, regret, attribution. Evolution has invested a tremendous amount of resources in this language, which sounds screwy, but we communicate so so frequently with it. There must be some advantage to that. Well, what's the alternative? And I wanted to demonstrate the alternative in terms of the robot world. Imagine that you have a team of robots playing soccer, and you ask yourself whether they will play better if you equip them with a language, with a vocabulary of credited blame. And I think they will, for reasons that I'm going to show. 3 reasons. A player made a mistake, and he didn't pass the ball to another player, and the goal wasn't scored, and we lost the game. Okay? Now comes the coach and says, you made a mistake. You should have passed the ball, we lost the game on account of you. You're going to sit on the bench for the next 2 games. Okay? Does it make sense? First of all, this information is being used every day. That's how people talk. Players blame each other. Where does the information come from? It comes from a coach. The coach has information that the players do not see. The coach was able to see that the other player was able to receive the pass. Right? So here's the reasons why we communicate in such a crazy language. It comes from an agent which has the same structure as we have. The coach cannot tell the player what to do in terms of the neural activation of the player. This is beyond the ability of the coach. The coach talks human language, and human language communicates through this window that we label the box, the software box, which contains the picture of the world and picture of yourself. Okay? So the coach can only communicate an improvement to the player in this crazy language of credit and blame. Okay? I'm coming to the end now. How does the coach say it? He say it in terms of, you're going to sit down on the bench, you should have passed. He doesn't name the missing neural activation that would have improved the performance. Why? Because he let the players himself figure out what software improvement is needed in order to improve the game. Who is more familiar with one's software packages? The player himself, the agent. Therefore, he gets the instruction, go ahead and do the improvement yourself. The same thing that Turing envisioned. The experiment with the act of intelligence to speed up. And the third point that I want to make is, if the coach can give instructions to a player for improvement, why can't the agent himself or herself come up with the same conclusion? After all, the agent has a picture of the world, picture of his own performance. Okay? He can reason out and say, counterfactually, I should have done better. And that, I think, is an opening to a new type of machine learning, where a machine not only learns to respond to evidence, but to respond to its own model of the world, model of its ability, its own agency, and come out with, how should I improve my software in order to play better? Thank you very much.
Thank you very much. In the interest of times, I think we'll proceed right to the reception, which is in the Conan room, which is right behind this auditorium. Thank you very much for coming. It was a really fascinating talk. I think we all enjoyed it very much.
Thank you very much.